start today's lecture. Okay. Okay, so we're continuing on with the reactivity. Here you go. So we're continuing on with the reactivity of alkenes. So another very prolific reaction that is utilized on even the ton scale in industrial processes is hydrogenation, which is the insertion of hydrogen, which is H2, onto an alkene. It is functionally the syn addition of hydrogen to an alkene. So in terms of the mechanism, in terms of the process involved, molecular hydrogen absorbs onto your catalyst bed. Then your hydrogen binds to your catalyst. Your alkene binds to your catalyst. You end up with a partially reduced intermediate, and then you generate your alkane plus your regenerated catalyst. Now, if it seems like we're being slightly ambiguous with the mechanism here, it's because this mechanism involves metal complexes and metal complex reactivity that will be covered in later organic classes. What I want you to appreciate for hydrogenation is that hydrogenation occurs with syn stereochemistry, and it's sensitive to the stereo environment. Remember our example, we saw pinene before in hydroboration. The top face is blocked by our methyl group, and so addition of hydrogen occurs from the more accessible alkene face. And what is the more accessible alkene face in this case? The top or the bottom? Where are we going to insert hydrogen from? The top or the bottom? So the top is blocked, has this bulky group. So what's the least hindered face? So I can either approach from the top and bump into this methyl group, or I can approach from the bottom. What face is least hindered? The bottom. And that's why we observe syn addition of hydrogen of H2 from the bottom. Okay, let's keep going. So the main thing, this is structural, this is not mechanistically related, but in terms of stereochemical outcome, it's somewhat related in terms of stereochemistry and stereoselectivity to hydroboration. Okay. Now, the interesting thing about hydrogenation, and we're not going to delve into too much detail in this class, but if you modify your catalyst and your ligand, you can end up generating enantioselective hydrogenation products. So this is covered more in upper division organic courses, but if you carefully choose your ligand, which are your species bound to your metal, you can end up inducing enantioselectivity during these hydrogenation reactions. Okay, so let's look at a few examples. Let's look at a few examples and let's try to predict the products for each of the following reactions. And if more than one enantiomer is generated, indicate each product formed. Okay, so let's do this first case together. So we have addition of hydrogen in a syn fashion. So I'm going to redraw my reactant. It's symmetrical, so we don't have to worry too much. Okay, hydrogen inserts in a syn fashion. And we also generate the enantiomer. So just to show a model of what's going on here, allow me one moment to construct a model. And I encourage you to put together a model of each of these structures at home while I'm assembling this first model. Okay, here we go. Oops, let me get rid of these extraneous functional groups. Okay, so here is our alkene. We can approach with hydrogen from either the bottom face or we can approach from the top face. We're going to arbitrarily choose to approach from the bottom face, which is closest to the camera. And now let's draw our products after syn addition. Again, I highly encourage you to make a model each time you're asked to predict the products of a chemical reaction. Okay, so we've added hydrogen across our alkene. And now all we have, oh, whoops, sorry. I have it pointing the wrong way. Whoops. Let me match the view exactly. Sorry, the camera's mirrored. Here we go. So we've added hydrogen across our alkene. And now all we have to do is just draw what we see. Are these hydrogens, when they add from the bottom face, are they pointing towards us or away from us? Are these hydrogens pointing towards us or away from us? Towards. That's why we draw them with wedges. The alkyl chain, this methyl, is pointing up in the plane of the page. So that's why you draw it pointing up. And we also generate the enantiomer, which would look something like this. Okay, let's take a look at another example. So we have the following alkene.
Professor, I have a question.
Yes.
So how would you know if it's gonna generate an enantiomer? Is it because there's a top and a bottom and you can attack on either?
Exactly.
Okay.
Yeah. So inherently in these processes, because both of the faces are equally accessible, you can always attack from both the top and the bottom face. And those in turn generate a mixture of enantiomers in most cases.
Oh, okay. So there's cases where it wouldn't have one.
Yeah, and such as the example with pinene, where one face is substantially more hindered than the other. So you can't generate a mixture of diastereomers or enantiomers.
All right, got it. Thanks.
The other case where you wouldn't generate an enantiomer is if there's already a stereocenter in the molecule, because then you wouldn't be inverting all of your stereocenters. Like, so for example, if there was like an OH here, then we'd be generating a mixture of diastereomers instead of enantiomers.
Okay, got it.
Perfect. Okay, so let's look at this next example. So this is an E-alkene. And let's try and predict the stereochemical outcome. And the way that I like to go about, especially straight chain alkenes, is I like to draw out all my hydrogens. Okay, so now that I've drawn out all my implied hydrogens, so I can add H2 from the top or the bottom face. We're going to arbitrarily choose to add it from the top face. And then we're just going to draw out our products from the sawhorse perspective, or pseudo sawhorse perspective. Okay, now here's a really interesting question. So if you look at centers A and B, is center A a genuine stereocenter? Is center A a genuine stereocenter? Is center A chiral? No, it doesn't have 4 different substituents. So then if we redraw this molecule, we have a mixture of 2 potential enantiomers. But in this case, we've only generated 1 stereocenter. So it's always important just to pay attention to whether or not you're generating a genuine stereocenter. Okay, so let's look at a model of this. I find the models often help people visualize these reactions, and it's often easier to understand how we obtain these drawings by looking at a model and considering both of the potential approaches for our hydrogen. Okay, so let's take a moment and let's build a model of this structure, and let's entertain both of the possibilities for hydrogen addition. So first and foremost, here is our molecule exactly reproduced according to our drawing. Now hydrogen can attack from the bottom or the top face. That's why we get a mixture of enantiomers. And let's arbitrarily choose, let's attack from the bottom face. So let's now look at the product after attack on the bottom face. Allow me one moment to put together the model. Okay. So we have added hydrogen from our bottom face. We now have the following structure. In order to make it a little bit easier to visualize, what we're going to do is we're going to turn our structure sideways so we can clearly observe the zigzag pattern of our alkene. And then all we're going to do is we're going to draw what we see. So in terms of our key stereocenter, so looking at this stereocenter right here, is our hydrogen pointing towards us or away from us? Towards us, exactly. So after treatment with hydrogen, if our hydrogen attacks from the bottom face, we generate the following product. And if we're just staring at our model exactly as drawn, we have our hydrogen in the front, our methyl in the back. And one thing that I really want you to note, when you look at this structure here, entertaining the attack from the bottom face, I want you to make sure that you draw your alkene chain exactly as indicated in the model. because if you start inverting your chain or changing the orientation of the chain, you may accidentally invert a stereocenter. Does everyone see how we got the following product from the tack of the bottom face? And does everyone notice how if we compare it to our attack from the top face, the stereochemical outcome is different? Can everyone see how these two facial approaches yield two different products and two different stereochemistries? Does that make sense to everyone? Are there any questions? Okay. So first, here's our product from the attack on the bottom face. The hydrogen is pointing towards us, the methyl's away from us. Here is the product after the attack from the top face. And let's see if you can catch the Here we go. So here's the product after the attack from the top face. And as we can clearly see, the methyl is pointing towards us. I see what happened. So the camera ended up flipping the perspective. The methyl is in front from the bottom face attack. The methyl is in the back from the top face attack. It's two facial approaches, two different products, two different relative positions of the methyl group. Let's look at another example. So we're going to look at another addition reaction to alkenes, this time the addition of carbines to alkenes. So a carbene functional group is of the form R2C. So this carbon has a lone pair and an empty p orbital. So a carbene has a carbon that is electron deficient, and it has a lone pair that is able to function as a nucleophile. So carbines overall are electron deficient, and they react with nucleophilic alkenes. So I like to think of carbines as like plus minus. They have an electrophilic empty p orbital and a lone pair that is able to function similar to a nucleophile. So in terms of how these carbines are generated, they're commonly generated from chlorinated solvents, chloroform being the most common solvent for generating dichlorocarbines. Would anyone like to comment as to why chloroform is particularly useful for generating carbines if the first step is deprotonation? What are these chlorines doing? What is the purpose of these chlorines? So for example, if I compare chloroform versus dichloromethane, what is the main difference? So inductive effects, and what do these inductive effects do? Do they make it easier or harder to remove our proton? Easier, yep. So in terms of pKa, the pKa of chloroform is less than dichloromethane. So it's easier to remove this proton. So inductive effects. Increase proton acidity. Okay, perfect. So after deprotonation, chloride leaves and we generate this dichloro carbine. Notice that it's a neutral species and it functions as an electrophile in reactions with electron-rich alkenes. So in terms of the mechanism for cyclopropanation, so in terms of our mechanism, let's look at a textbook alkene. Let's look at a textbook alkene. Once we have generated our dichlorocarbene, I'll show the steps here just for your reference. So if we have chloroform and sodium hydroxide, so in our first step, hydroxide is going to remove a proton. Then chloride leaves, and we generate our dichlorocarbene. Now that we have our dichlorocarbene, we end up with a concerted syn addition from either the top or the bottom face. And that in turn generates a chlorocyclopropane. We also, of course, generate the enantiomer if our dichlorocarbene approaches from the bottom face. So mechanistically similar to how we generate, for example, a bromonium ion. Syn addition from one face to generate a three-membered ring. So alkene addition of dichlorocarbene is stereospecific. So for example, if you have a cis alkene, you end up with the cis disubstituted cyclopropane. So notice how our alkyl substituents are cis starting out in our alkene, and our alkyl substituents end up with the same relative stereochemistry. If you have a trans alkene, you get a trans disubstituted cyclopropane. So let's show the trans alkene. So let's suppose we have our trans alkene. So cis, otherwise known as Z. And let's look at our E, or our trans alkene. We would expect to observe the trans cyclopropane product. And the nice thing about thinking about these reactions in terms of cis and trans alkenes, the only alkenes that you'll ever see are cis and trans. So if you know the stereochemical outcome for a cis and trans alkene, you can predict the product for any alkene substrate I give you. Does that idea make sense? So whenever you're thinking through this reaction, just like we've been doing throughout this note set, always focus on what is the stereochemical outcome of a cis alkene? What about a trans alkene? Okay. Does everyone see the clear difference in stereochemical outcome for these two reactions? Okay, perfect. In this case, it was added from the top face. Because as we notice, the dichlorocarbene is on the top face of our alkene. And of course, you also generate the enantiomer. Okay, so let's try to predict some products. So let's try to predict the product for the following reaction. So starting off, we're just dealing with our simple standard alkene. So first things first, I'd like to draw out my substrate. I like to draw out my dichloro carbine. And then I show the concerted attack. And in turn, supposing that we are attacking from the top face, our dichlorocarbene is on the top, while our hydrogens are on the bottom face. We also generate inherently the enantiomer, which is the product from the attack on the bottom face. Does this make sense so far to everyone? So you can think of this like your typical Z alkene. Okay, looking at the following molecule, we have an E alkene to work with. So if we draw out both of our hydrogens, now, just like we did with hydrogenation, we're going to look at our alkene. We're going to draw out all of our implied hydrogens, and we're going to entertain an attack from the top face. Whoops. Okay. Now we draw our product in a pseudo sawhorse orientation. Okay. And in this case, we don't have to do really any rotation of our view. It's very clear what species are pointing out of the page and what species are pointing into the page. Depending on how you rotate this molecule, you can draw your products in slightly different ways. So we generate the following product plus the enantiomer. And the enantiomer is generated from the attack on the bottom face. Now, of course, you can redraw this molecule. You can redraw this molecule so that your substituents pointing behind this cyclopropane are in the back of the page, and the substituents pointing in front of the cyclopropane are in front of the page. Again, there are many ways to rotate a molecule. Would anyone like to see a model for this reaction? Would anyone like to see a model? Let's show that just so that way we're clear. Let's take a look at a model for this. I find it often is incredibly helpful to visualize these different products and visualize how to rotate these molecules correctly. So let's start first and foremost just by visualizing. So here's what our molecule looks like. So I made a one-to-one model. Now let's introduce our dichloro carbine. And hopefully I don't break a model kit because these cyclopropanes are incredibly strained. Okay, so our carbene, our dichlorocarbene, can attack from the face closest to us or the face farthest from us. So I'm going to attack from the face that is, so if we're respecting our drawing, we're attacking from the face farthest from us that we'll consider the top face, okay? So we're following our drawing exactly. We're attacking from the top face. Does everyone see that? Is everyone following what we're doing? We have our alkene, we're attacking from the top face. Does that make sense to everyone so far? Okay, we're following our drawing one-to-one here. I'm not changing anything from our drawing at all. Okay. Now let's put together our carbene. And as you notice, you can immediately tell the cyclopropane is very strained by the fact that your model kit will start wanting to fall apart when you try to put this cyclopropane together. Note, carbene formation is also one of the reasons why you have to be pretty careful when handling chlorinated solvents. Because if you expose them to the wrong reaction conditions, you can make a carbene, and those reactions can get out of hand pretty quickly. So I'm still putting together our model, making sure that I'm following. Here we go. So here is our model after we have added our dichlorocarbene from the face farthest from us, from the top face. Now, if we look at it from the perspective, shown here, my question to all of you, looking at this hydrogen right here, is it pointing out of the page or into the page? Is the hydrogen right here pointing out of the page or into the page? Pointing out. That's why we give it a wedge. The ethyl group in the back, whoops, sorry about that. The model just loves to fall apart here. This ethyl group in the back, is it pointing towards us or away from us? This ethyl group, compared to the hydrogen, is this ethyl group pointing towards us or away from us? So compared to this hydrogen, is the ethyl group pointing towards or away from us? Pointing away from us, and that's why we give it a dash. Now, of course, there are many ways to rotate. There are many ways to rotate this molecule. If we view this molecule from this perspective, as we have clearly drawn, we notice we have our hydrogen and ethyl group on the left. We have our cyclopropane pointing out of the page, and we have our hydrogen and ethyl group on the right. Does that make sense to everyone so far? Does that make sense to everyone visualizing these structures? Okay, perfect. So we generate two products, the desired compound as well as its enantiomer. So there are multiple ways to generate carbenes. There are multiple ways to generate carbenes, one of which is known as the Simmons-Smith reaction. In this case, we aren't utilizing a dichlorocarbene. Instead, we're generating just a non-functionalized carbene. So in this case, we take diiodomethane and treat it with a zinc copper alloy, which in turn generates our carbene species. Again, the stereochemical outcome is identical. Syn addition from the least hindered phase. Now, we can further functionalize alkenes to produce additional functional group handles. So the most common of which is epoxidation, which of course installs the functional group of an epoxide, which is a cyclic three-membered ring containing an oxygen functionality. One of the most common reagents for epoxidation is metachloroperoxybenzoic acid, or MCPBA for short. So with any peroxy acid, it follows a one-step mechanism for epoxidation, where you have attack of your alkene on your electrophilic oxygen, an attack of the oxygen on the other carbon of your alkene, followed by a rearrangement of electrons to remove the proton. So this all occurs in a one-step concerted process, and in the end we generate our epoxide and a carboxylic acid. Now, the interesting thing about this reaction is that the addition occurs from the least hindered phase. So you can get stereoselectivity for certain products. So this is just a note. You won't be tested extensively on facial selectivity in this course, but I just want to bring this idea up because it's a common theme of later organic classes. Okay, so once we have our epoxide, we can utilize a second reaction in order to generate diols, which are sets of alcohols in adjacent carbons with a slightly different stereochemistry than our previous methods. So acid catalyzed epoxide opening is a wonderful method to generate a trans diol. This is compared to, so we can access trans diols. So our alcohols have opposite stereochemistries. So epoxide opening under acidic condition proceeds with Markovnikov selectivity and anti-stereochemistry. Further, if epoxide opening is performed with an alcohol nucleophile, the nucleophile is incorporated at the most substituted position, the most cationic or most cation-like carbon. So again, similar trends to what we observe for what process? What reaction does this remind you of a lot in terms of stereochemistry and regiochemistry? What does this remind you of? Where we have attack of our nucleophile, in this case our alcohol, at the most substituted carbon, resulting in a trans stereochemistry. What reaction does this remind everyone of? We went over it last class session. Let's try to draw some patterns. What does this remind you of? We're opening up a cyclic intermediate and the attack occurs at the most substituted carbon. What does that remind you of? And I'll start drawing just a hint structure. Is acid catalyzed epoxide opening mechanistically almost identical to halohydrin formation? Mechanistically, is there anything really different occurring between halohydrin formation and acid catalyzed epoxide opening? Are we both attacking a cyclic intermediate to generate a product with trans stereochemistry and with Markovnikov selectivity? Are these two reactions almost completely identical mechanistically? Yes. Okay. So the reason why I'm bringing this up is you want to be able to draw parallels between the reactions that you observe. Does that make sense to everyone so far? Okay, perfect. So same rules for halothermification apply to acid catalyzed epoxide opening. So let's look at a few ways to reverse selectivity. So under basic conditions, we have a reverse Regio selectivity. And this is why epoxide opening is pretty cool, because depending on whether you're running it under acidic or basic conditions, you get different regiochemical outcomes. So under basic conditions, you get anti-Markovnikov regiochemistry and anti-stereochemistry. So this is a stereotypical SN2 reaction, and the nucleophile attacks at the least hindered carbon. And most importantly, this reaction under basic conditions does not occur efficiently for tertiary carbons. We still have the trans stereochemistry because we're attacking from the opposite face to our epoxide. So, just to showcase this idea very clearly, under acidic versus basic conditions, under basic, we deal with anti-Markovnikov. Under acidic conditions, we observe Markovnikov selectivity. Why? Under basic conditions, we are concerned about steric hindrance. Under acidic conditions, we are concerned with carbocation character. Does everyone see the difference between acidic and basic conditions? And is everyone starting to see why there's a difference? Under basic conditions, we are not generating a carbocation or carbocationic-like species. Under acidic conditions, the carbocation character of our carbons directly affects the regioselectivity and the site that your nucleophile prefers to attack. Okay, so let's look at a few examples and let's try to predict the products from each of these reactions. So we'll do the first one together and the second one I'll have you do independently. So first things first, we have our typical Z alkene. Okay, I'm going to draw out my peroxy acid. So this is peracetic acid. This is why you're often told not to mix vinegar and hydrogen peroxide, because this generates quite a strong peroxy acid that can function as an oxidizing agent, and it's quite corrosive for that matter. Okay, so we have concerted attack. So I'm going to draw my alkene attacking the peroxide oxygen, my peroxide oxygen attacking my alkene. We have a shift of electron density and an intramolecular proton, I guess you can call it a proton transfer. Okay, this all occurs in one step in a concerted process. And this time we're going to propose an attack from the top face. After attack from the top face, we generate the following epoxide. So after step one, we have the following epoxide in place. Now, what we're going to do is we're going to consider under acidic conditions what will happen next. Well, first and foremost, if we have H3O plus sitting around, we're going to protonate our epoxide, and we're going to generate our protonated epoxide species. My question to all of you is, in this second step for acid catalyzed epoxide opening, what is our nucleophile going to be? What is our nucleophile going to be? In our second step, if we have H3O plus, what is our nucleophile going to be? Just a lone oxygen atom? Yeah, you're right that oxygen is our nucleophilic atom, but what is the identity of our nucleophile? H3O plus. An acidic solution of what solvent? An acidic solution of what solvent? When I say H3O plus, what is sitting around? Water. Exactly right. Water. Exactly right. Perfect. Okay. So let's look at our alkene. Let's look at our alkene. So first things first, we're going to make a model. Okay. Whoops, sorry. So here is the alkene as we have observed. Here's the alkene as we have observed in our drawing. Okay, so now what we're going to do, and I'm just going to represent our peroxy acid with an oxygen. So we're going to attack our alkene from either the top or the bottom face. We presupposed an attack from the top face in this example. So let's now look at our epoxide from this process. Let's look at the epoxide generated from this process. And the reason why I'm showing this step by step is so that way we don't get anything mixed up. So that way we don't get anything mixed up in this process. So let's look at our epoxide, and then we'll entertain how water will attack. We'll think about how will water attack this position. Okay, so, whoops, one moment. Let me get this just right so that way we can consider what's going on with our epoxide. So we generated our epoxide, and now for our next step, let's first take a look at the epoxide generated, and let's think about how our epoxide will be attacked by water. Okay, so here we go. Here is our epoxide. Now, we have two potential sites on the bottom face. We can either attack at the least substituted or the most substituted site. Which site will we attack at? The least or the most substituted under acidic conditions? The most or the least? What site will we attack at under acidic conditions? Under acidic conditions, we're looking at carbocation character, and what site will have more carbocationic character? The more substituted position or the least substituted? The most. So we'll attack at the most substituted position. Now, we'll be attacking if our epoxides on the top face, are we attacking from the top or the bottom face? Are we attacking from the top or the bottom face? The bottom face. Okay, perfect. So now let's observe what product do we get. Okay, so we've attacked our epoxide from the bottom face and we generated the following product that we draw in pseudo sawhorse arrangement. Now, if we're drawing this in a more linear form, what we're going to do is we're going to take our alkyl chain and we're just going to view our alkyl chain and we're going to draw it exactly as we see it. We're going to draw our alkyl chain exactly as we see it. So we're going to adjust our alkyl chain so it's a straight chain like a zigzag, and we're just going to draw what we see. So we have our 5-carbon chain. Now looking at our first alcohol, our alcohol on the left, is this alcohol going out of the page or into the page? Is this alcohol going out of the page or into the page? Is it pointing towards or away from us? Is this alcohol pointing towards or away from us? It's pointing towards us. Okay, and the methyl group is pointing away from us. Now for our second alcohol, looking at this second alcohol, is it pointing towards or away from us? Towards us, okay? Perfect. Now, just to showcase what we did, here. So initially, we had our trans addition product. Our trans addition product looked something like this. Now, here we can clearly see both of our alcohols are trans. We then rotated our carbon-carbon bonds. To give us a straight chain alkene, which we drew as follows. Okay, so there are many ways of drawing out these structures. If you prefer to draw your alkene like this, that's no problem. I always like to convert my structures into a nice straight chain because that's often how structures are drawn. It's a little awkward when you have these non-realistic bond angles or non-realistic views. But you're more than welcome to just draw your alkene shape and then draw your alcohols as trans to each other. That's more than okay. Whatever you prefer. Just as a correction in this case, so the alcohol pointing up would be up. And the alcohol pointing down would be down. There we go. So however you prefer to draw your products from this epoxidation epoxide opening, either is okay. I just want you to get in the habit of rotating your structures to these straight chain alkenes, because that's often how questions will be phrased on the ACS. Does everyone understand this example? Does everyone understand the stereochemical outcome from this example? Any questions? Okay, so let's have you work on this next example. I'd like you to draw and predict the products from the first epoxidation step, as well as to draw and predict the products from the second acid catalyzed epoxide opening step. So let's take about 4 to 5 minutes to work through this problem, and then we'll come together as a group to discuss. And don't be shy to break out the annotate feature when you're proposing a solution for the following example. And there's plenty of space for 2 people to attempt to annotate, and don't be shy to make a model. So this is an example where we're looking at a Z alkene. And we'll come together to discuss in about 4 to 5 minutes. And really don't be shy to break out the annotate tool and try drawing out your proposed products from this reaction. And when in doubt, make a model. We'll discuss in about 4 to 5 minutes. And don't be shy to message me with your proposed questions while solving this problem. I really want to give you a few minutes to try out this type of problem, as you'll see similar product prediction problems on your exam. Any questions so far? Does anyone want to try proposing the products from this reaction? The structure drawn in pink looked fine. And the mechanism drawn in red looks spot on. Perfect. Yep, protonation step looks good. Yep. Yep. And could you draw the intermediate right before? So this is perfect so far. Could you draw your product with dash wedge notation? Just so that way I can check the stereochemistry. But otherwise, it looks good. In terms of regiochemistry, both of the sites are equally substituted. Would the alcohols be on the same face or opposite faces? Yep. Yep. Perfect. Looks good. So let's talk about this example. So that was perfect. So let's talk about this next example, and let's go through each of the steps. So first and foremost, as was very correctly drawn, we have our first epoxidation step using our peroxy acid. We generate our epoxide, of course, presuming attack from the top face just for simplicity. Okay, so just to show where we're at so far, here's our alkene. We attacked from the top face. We generated the following epoxide. We can attack from either face. Let's just arbitrarily choose. So, well, first things first, we're going to protonate. Once we've activated our epoxide for attack, then water is going to attack from the opposite face of our epoxide at either carbon. Let's just arbitrarily choose to attack the carbon on the left, just to make it easier to draw. We're attacking from the bottom face opposite to our epoxide. Let's now look at the product from that reaction. Okay, so now from our perspective, what we're going to do is we're just going to draw out our alkene chain and both of our hydrogens. The alcohol on the left, is it pointing towards us or away from us? Is this alcohol pointing towards or away from us? Away. Oh, this one right here? Yep, it's pointing away. Yep, so we'll draw this with a dash. And is this alcohol on the right pointing towards or away from us? Towards, yep. There we go, perfect. Now, of course, before we completely finish this mechanism, we do need to deprotonate our alcohol, but that's a pretty minor step in the process. So we generate the following product. Now, with a little bit of rotation, if I want to get like a zigzag straight chain alkene, I just rotate one of my bonds and then I draw what I see. So this structure is equivalent to the following structure. So where we have on our left, we have the hydrogen in front, our alcohol in the back, and on our right, we have the hydrogen in front, and our alcohol in the back. So these two structures are identical, mind you. All I've done is just rotated one of my bonds, okay? So these are just two ways of depicting the same structure. I personally like keeping the alkene skeleton fixed because it clearly shows that your two alcohols are trans to each other. Does that make sense to everyone? Is everyone comfortable with these examples so far? Can everyone?
Professor?
Yes.
So on the test, you're gonna want the straight chain.
You can draw both.
Okay,
you can draw both.
Okay.
But in terms of identifying reaction products, especially on the Canvas quizzes, you may see the straight chain alkene shown, and you may see it as well on ACS exams. So you should be able to recognize that these two structures are identical and representing the same reaction outcome. Does that make sense?
Yeah.
Perfect. So let's keep going now, and let's look at syn dihydroxylation. So syn dihydroxylation, so both of our alcohols end up on the same face. Now the method proposed in the book is pretty old school. They use stoichiometric osmium tetroxide, then sodium bisulfite. So it occurs via a cyclic osmate diester intermediate. So osmium tetroxide looks a little bit like this. When you have your alkene, you end up with a concerted attack onto the alkene, and you generate the cyclic osmate ester that is then cleaved with sodium bisulfate or other reducing agents. You can also complete this reaction with potassium permanganate, but I would be advised that this reaction is not very clean if you use potassium permanganate. So osmium is your go-to method to generate a syn diol, where both of your alcohols are installed in the same phase. Now, as always, we're going to look at an E and Z alkene, and I'm going to do this first example, and you'll do the second. So First and foremost, I'm going to draw out each of my hydrogens. I'm going to propose that attack occurs from the top face. I like drawing out the cyclic osmate ester, if only because it helps me very clearly see that both of my alcohols are on the same face. You won't be responsible for drawing the cleaving step for this mechanism, but it really helps me see that both of my alcohols are on the same face. And after reductive cleavage with sodium bisulfite, we end up with the syn diol. So just to show what that looks like on paper, here is our structure. Dihydroxylation. Dihydroxylation can occur from the bottom or the top face. We're arbitrarily going to choose the top face. So here is our structure after dihydroxylation. Notice both of our alcohols are pointing away from us. Okay. So in our model, we're entertaining the approach from the opposite face, which would have yielded the following diol. As we can see by the fact both of our alcohols are pointing away from us. If we wanted to get a straight chain alkene, all we do is rotate our model slightly. We now just draw what we see. So we use this symbol to say that they're equivalent. And as we can clearly see, after rotation, are both of our alcohols pointing towards us or away from us? Are our alcohols pointing towards us or away from us in this case? They're pointing away from us, exactly right. There we go. So these two potential structures are enantiomers. And they're the products from the attack from either the top or the bottom face. Any questions on this example after we've observed the model for these reactions? Now, to test everyone's understanding, I'd like you now to look at the following Z alkene and predict the products from osmium catalyzed dihydroxylation. And we'll discuss in about 4 to 5 minutes. The sulfur doesn't end up incorporated. Essentially, this bisulfite is a reducing agent. And it cleaves the bisulfite cleaves the bond between your diol and the osmium complex. It's just a reducing agent. we're sort of avoiding going into too much detail about that mechanism, as mechanisms associated with metal complexes are typically reserved for later semester organic classes. The main thing that we're focusing on for this toolbox of reactions is understanding from the mechanistic perspective why certain products are generated, and then from there using the selectivity for all of these reactions to begin to selectively generate products we want from chemical reactions. So what reaction do I use to get what product? Or why does this reaction give me these products? That's our goal in this chapter. So don't be shy to break out the annotate tool and draw out the product from this dihydroxylation reaction. And then you kick one of the bonding pairs of electrons to the osmium, because osmium is functioning like an electrophile. It's gaining electron density from your alkene. It's oxidizing the alkene. But overall, looks good. Yep. Perfect. And you can skip the osmate ester cleaving step and you can just draw the diol. But yes, the stereochemistry looks good for the diol. Yep, everything looks good. So what I'm going to do is I'm going to clear and I'm going to provide the instructor solution, but the stereochemistry and dash wedge assignment looks good. So let's take a look at this example. So first things first, we're going to draw out our alkene with both of our hydrogens. We're going to draw out an approach from the top face. So we generate our syn diol. So just to show everyone what the syn dihydroxylation product will look like, we have the following product. Oops, sorry, wrong way. Here we go. With both of our alcohols pointing up. If we want to generate a structure in dash wedge notation, all we have to do is rotate our bonds. So this structure is equivalent. If we wanted to draw a straight chain alkene, it would be equivalent to the following depiction. Either response would be correct on an exam. Any questions on this example? If not, what we're going to do is we're going to take a quick 10-minute break and then resume lecture in laboratory.